Welcome back, everyone. Let's take a look at the sectorial scan, or S-scan, on a phased array display. What exactly is it and what is it made up of? First up, thank you, Markus Steffen, my friend in this German band Subsignal, one of my favorites, and I asked him for a shirt, and I said I promised to wear it in a video, so he sent me a shirt, so thanks, Markus. All right, now, right down to business, I've got a Vermon 10 megahertz 64 element probe. I'm going to use 32 of these. I've got my Sonatest Veo, and I'm going to show you exactly what it is that you're looking at when you're looking at a sectorial scan. They also go by the name of azimuthal scan, but I don't think anybody ever calls it that anymore. It's a sectorial scan. Looks like a sector out of a piece of pie. Let's grab an IIW block. It has a 1.5 millimeter side drilled hole, and I'll take this phased array probe, but what I'll start off with is just the 60-degree angle, and that's all we're going to look at. That's the only thing you'll see on the screen. So it's kind of like just doing conventional mono element UT at just a fixed angle. And you can see here that as I move the probe back and forth, you get it to peak right around in here. And that means the hole is at the center of the beams. The beam is shining down into the steel at 60 degrees, and the maximum amount of sound is coming back to the probe. Now, we can also, with phased array, of course, use many angles. So if I hit the view cursor once, I'll move up to the next angle. I've set that at 65 degrees. You can see at this point, the beam doesn't really see much of the hole at all until I move the probe back slightly. Now the center of the hole is in the middle of the 65-degree portion, and in a similar fashion I can move up to the 55-degree and push the probe forward until we peak the beam right about here. The sectorial scan is just a stack of all of the A scans in the range of angles that we're using in our focal law. So as I move the probe back and forth, and the little reflection from the hole is moved through all of the range of angles, each one of those actually represents a separate A scan. And here's another way to look at it. Here's an S scan with the side drilled hole. I put 3 angle cursors on here. The middle angle cursor actually strikes the hole square on, so I get a good response. And I put a couple angle cursors on either side just to show you that even though those actual angles would miss the hole, because ultrasound has some width to it, it's not a laser beam, even though sometimes we draw it like a line, you will get a little bit of a response just off the periphery of the beam. So here we can see that in the upper right hand side, that's the 55 degree, the one that hit the hole right on, and the other two on the left are, we just kind of missed the hole, so it's just the edge of the beam that's picking it up, so they're a little bit lower. Now, like I said, it's kind of a stack of A scans, so here I've gone and taken all of the A scans and tried to kind of smash them together and make them transparent to let you know what's going on. Kind of looks like this, which would be very difficult to look at or interpret. So what we do is we convert the amplitude of the A scan into color, and we end up with this. On the S scan, you'll notice a lot of the time we're looking at the weld upside down. Now that is because when we push sound into the weld, we can't usually get to where we want to go until we take a bounce off of the bottom or on a vessel or pipe. We call that the ID. So that's why everything looks upside down. You can imagine that when you're standing in front of a mirror and you have maybe Subsignal written on your shirt, it doesn't say Subsignal, it says everything backwards. And it's the same way with ultrasound. Everything in the second leg, or after the first bounce, looks upside down or backwards. You could take the first reflection and flip it up so that everything stayed within the bounds of a piece of steel. Now, that is interesting, but not so useful most of the time for analysis, because then you have overlapping pieces. So it is easier most of the time just to have the sectorial view go all the way down and just keep flipping the weld profile every time the sound takes a bounce. On a real weld, this is a Flaw-Tech weld specimen. We have an ID root crack on the near side, and as I move the probe back and forth, you can see all the different little reflections and crack facets that light up. And on the first leg, before the reflection, my weld profile is right side up, and on the first reflection, or the second leg, the weld profile is upside down. And we use both of those to give us an idea of the characterization and the height of the flaw. So if you weren't familiar with what a sectorial scan was, I hope that answers your question. If you did like the video, please hit the like and subscribe buttons, and thanks for watching.